Part 2. We're shifting from outcome measures to production measures, and we'll cover 3 big categories in Part 2. Objective 4, kinematics, the description of motion. 3 measures, displacement, velocity, acceleration, and the distinction between linear motion and angular motion. Objective 5, EMG, the electrical activity of muscles. And while we're in the neighborhood, we'll also touch on kinetics, the forces that cause motion. Together, these 3 give you the production-side toolkit that biomechanists, motor control researchers, and increasingly clinicians use to look inside a movement.
Kinematics describes motion without regard to force or mass. The 3 core kinematic measures, displacement, velocity, acceleration, are nested derivatives of each other. Displacement is the change in the spatial position of a limb or joint during a movement. With motion capture systems, we attach reflective markers to the joints and track their XY or XYZ position frame by frame. Plotted over time, that's a displacement curve. See the first small graph on the slide. The wrist starts at one angle, swings through a range, ends at another. That's displacement. Velocity is the rate of change of displacement. The math: divide change in position by change in time. Velocity tells you how fast the limb is moving at each moment. Look at the second curve. When the velocity is 0, the limb isn't moving. When it's positive, the limb is moving in one direction. Negative, the opposite direction. Acceleration is the rate of change of velocity. Divide change in velocity by change in time. Acceleration tells you whether the limb is speeding up or slowing down, and how quickly. Look at the third curve. Big positive spikes mean rapid acceleration. Big negative spikes mean rapid deceleration. So 3 nested views of the same movement. Displacement says where. Velocity says how fast. Acceleration says speeding up or slowing down. Motion capture software produces all 3 from one raw recording. You just pick which to look at, depending on the question you're asking. For a PT analyzing a patient's reaching pattern, velocity tells you about smoothness. Acceleration spikes tell you about jerk and control. Displacement tells you whether the patient can still reach the target.
And the second big distinction in kinematics, linear motion versus angular motion. Both can be described with displacement, velocity, and acceleration, but they describe different things. Linear motion is straight-line translation. The whole body or a whole object moves the same distance over the same time. The diagram on the left shows a person walking across the room. That's linear motion. If you want to describe how the body progressed from point A to point B, you use linear measures. Angular motion is rotation about an axis, typically a joint. The diagram on the right shows a foot rotating about the ankle joint as the person takes a step. The foot itself isn't moving in a straight line, it's swinging through an arc. If you want to describe what specific limb segments are doing, you use angular measures. So the same walking motion gives you different analyses depending on what you're after. The body's linear progress across the room, the foot's angular rotation about the ankle, the knee's angular flexion and extension. All 3 are valid, all 3 answer different questions. As a clinician, say a gait analyst, you'll routinely use both. Linear measures to track stride length and cadence, angular measures to spot joint-level deviations like a stiff knee or excessive hip rotation. Now, the other 2 production tools in Objective 5. Kinetics on the left, the study of force as a cause of motion. Where kinematics describes motion, kinetics explains it. Newton's 3 laws of motion all involve force. The most useful equation in our work is F equals m times a. Force equals mass times acceleration. That means if you have kinematic data, the acceleration of a limb, and you know the mass of the limb, you can calculate force without needing a force plate. Or you can measure force directly with instruments. A force plate for ground reaction forces, a force transducer for muscle output, a strain gauge for tension. A particularly useful kinetic measure is joint torque, the rotary force at a joint. The graph in the textbook shows net knee torque during a drop-jump landing, and you can see how peak torque maps onto the moment of impact. For strength coaches and rehab specialists, joint torque is the gold standard for understanding loading patterns. EMG on the right, electromyography. Electrodes, surface or fine wire, pick up the electrical chatter of a muscle. When the muscle's not active, the trace is flat. When it fires, the trace gets dense and tall.
EMG tells us when a muscle activates. And when we record from multiple muscles at once, the sequence of activation tells us something profound about motor control. Look at the example in the textbook. A participant moves the arm on a go signal. The first muscle to fire isn't an arm muscle. It's the biceps femoris of the same leg, a postural muscle. Then comes the anterior deltoid, the arm mover. The body sets up its base of support before it moves the limb. That's an insight you only get from EMG. Practical applications. PTs use EMG biofeedback to teach patients to selectively activate or relax specific muscles. Strength coaches use EMG to confirm whether an exercise is hitting the intended muscle. Researchers use EMG to fractionate RT, as we saw in Part 1.
Part 2 summary. 3 lenses on the production side of performance: kinematics, displacement, velocity, acceleration, linear or angular; kinetics, force, joint torque; EMG, muscle electrical activity. Kinematics says what, kinetics says why, EMG says who fired first. Take those 3 slogans into Part 3 with you. That's where we leave the body for a moment and look at the brain, and then come back to look at how the joints and limbs coordinate.